Bismillahirrahmanirrahim. Assalamu alaikum ji. We're talking about neural networks. We introduce you to the concept of neural networks, which is nothing but just a bunch of neurons connected together. We also established a connection with our prior knowledge of perceptron and logistic regression. And then we defined the notation we adopt to traverse a neural network. And then this traversing is enabled by the so-called forward pass, which is just a bunch of equations which we can employ to traverse a neural network layer by layer. And then we studied activation functions for neural network. Since every neuron in the network is characterized by an activation function, we studied different activation functions which we can use in the neural network in hidden layers and also at the output layer, right? Okay, today we will focus on the learning of neural network parameters. Given the data, given the neural network, how can we learn weights and bias in different layers of the network? And this is enabled by a very famous, very popular method, back propagation. Learning of neural network parameters means we want to learn the weights that include weight matrices and bias vectors for hidden layers and output layer, given the training data. Before we move forward, we can quickly revisit the notation we defined for neural networks. We use capital L to denote the number of layers. Number of nodes in the nth layer is given by M superscript L in square brackets. So whenever we refer to this superscript in square brackets, we will be referring to the nth layer of the network. I assume you are comfortable with this notation now. A subscript I superscript L denotes the output of ith node in the nth layer. And if I stack all of these outputs in one vector, I can define a vector A superscript L, which is the output of the nth layer. What is the size of this vector? The number of nodes in the nth layer, which is M superscript L. Obviously, A superscript 0 is equal to X because we do not count input layer in the number of layers. Similarly, the last layer is my output layer. So A superscript capital L is equal to Y, the output. So if we talk about the weight vectors and biases for each node, so we use W subscript I capital L, the same notation. So this is the weight vector that is associated with the ith node in the nth layer. Similarly, B subscript IL, the bias for the ith node in the nth layer. If you zoom into this weight vector, so Wij, so jth entry of this weight vector denotes the weight that is associated with the jth input of the ith node. So we have studied this earlier, but I'm just revisiting here because we'll be using these very frequently in this video, so that you have a good understanding of or a good revision of these notations, right? As an example, we take 3 inputs, 1 output, 3-layer network in which we have 2 hidden layers and 1 output layer. So we defined these weight matrices and this bias vector. So these two contain all the parameters we need to learn for the layer 1. Similarly, W2, B2 correspond to the weights and biases which we want to learn for layer 2. And similarly, W3, B3 for output layer or for layer 3. So these are the parameters we need to learn given the training data. So this is a learning weights problem we have in hand. Okay, moving forward, we assume that we have a training data D given by, so we have a supervised learning problem. We have a label associated with each of the inputs. And we have inputs, the features in the D-dimensional space. and output we are assuming is a scalar, but nevertheless it can be a vector. But for the sake of convenience, we can assume that it is a scalar. And we have n data points. If we consider a network with d nodes, features at input layer, one output node, and any number of hidden layers. For such a network, we can define the loss function, assuming we have a regression problem. It will be simply a squared error, right? So y I tilde is the output given by the network for input xi, yi is the true label. You take a difference that is an error, you square it, and you sum over all the observations. This is a squared error. And we know why do we write this 1 over 2. So we're trained. Okay, if this is a classification problem, and we instead use log loss because the output would be representing probability for the case of classification problem, right? Nevertheless, if we have the loss function is continuous, whether it is a log loss or whether it is a squared error. So we can differentiate, and therefore we can use gradient descent to learn the weight matrices and bias vectors, right? Given our prior knowledge, we know that the output of a neural network is a composite function of the inputs, right? Because we're traversing input, we are feeding input, and we're traversing different layers of a neural network to reach the output. We know that output is a nonlinear function of a linear combination of the inputs from the previous layer, which are the nonlinear function of linear combination of the previous layer, and so on and so forth. Right? We can say output is a composite function of input. And we know that it is continuous, differentiable, and therefore we can use chain rule to compute the gradient. And in order to compute this gradient, we use a method which we call back propagation to implement the chain rule for the computation of gradient. Right? Okay, let me explain this back propagation method very briefly. And then we'll take a step forward, and we will see the mathematical details and how do we implement chain rule to compute the gradient using back propagation. So the idea is very, very simple. Okay, in back propagation, we know that if we have a neural network, we can compute the loss function using forward pass. How? For each input, we traverse neural network and we compute the output, say call it yi tilde for input xi. We know the true label for xi, and therefore we can compute the loss. So if we only have one input, we don't have a summation here. If we have n number of inputs, we can sum the squared error to have the loss, the total loss, right? So this loss is a function of, obviously it depends on inputs, but if you change the parameters that define your network, if you change the weights and biases, yi tilde would change. We can say the weights are the only parameters that can be modified to make the loss function as low as possible for a given input. Agree? How can we update the weights? Using gradient descent. If we have Wij L, what does Wij L denote? Ith layer, ith node of the lth layer, and j defines the weight associated with the jth input of the node. And we update as previous weight, we update it iteratively. So previous weight minus alpha times gradient of the loss function, partial derivative of the loss function with respect to this weight. This is gradient descent, right? So we want to compute this partial derivative of the loss function with respect to this weight. In fact, for every weight, and WLIJ, and also for every bias term. So the idea is we compute this derivative by back propagating the total loss at the output node. So we have computed this loss, which is at the output node. We back propagate this loss back into the neural network to find out what is the contribution of every node towards the loss. And that's why we call this method as back propagation. So we back propagate the loss in this direction, and we find the contribution of every node towards the loss. Right? Okay, given this formulation of gradient descent, we can say that learning of weights or learning of neural network parameters reduces to the question of calculating gradient or calculating partial derivatives of loss function with respect to every weight and with respect to bias for each node. Right? Okay, before we define backpropagation for our vector notation, I will introduce you to one simple example in which we will work out these partial derivatives, or we will work out the backpropagation. Okay, assume that we have a two-layer network with two neurons in the hidden layer, two inputs and two outputs network. Right? And we assume that the activation function is sigmoid, right? It simply means G of Z is sigma of Z. So this is the neural network we have. We have two inputs, X1, X2, which are A10, A20, and then we have these weights, the layer 1, layer 2. So one hidden layer. This is the output layer. So this is the output layer. And A12 is equal to Y1, and because A22 corresponds to the output of the second node in the second layer, and this is the output layer, and therefore Y22 is equal to A2, right? Okay, we assume that we are given some training data. We're given just say 1 point. So one input is 0.05 and 0.1. We have two inputs. The output, we get the outputs 0.01 and 0.99. So these are the given outputs, or the labels are the true values for these inputs. So we assume that we initialize the weights. By the way, I have not shown the biases here. We know that the biases are hidden in each layer, right? This could be B1, similarly B2, first layer, and so on and so forth. We assume that we're given these initial values of weights and biases, right? So we initialize weights. So these are the parameters of the first layer, and these are the parameters of second, sorry. It should be, my apologies, it should be B2, 2, and B1, 2. Okay. So given these weights and given inputs, can we find output? Obviously, yes. We can traverse the network, forward pass, to obtain the output. What are the equations? In fact, everything's written here. Right? And we know that we can determine at every node pre-activation output, which is simply a linear combination of inputs plus bias, pass this through an activation function, which is sigmoid in our case, in this example, and we obtain A11, right? And if I compute this for every node, and it traverses the network. So the pre-activation output for the first node in the first layer would be, so W11 X1 plus W121, sorry, W112 with X2 plus the bias for the first layer. And when you compute using the values, you get this value. And when we pass this through an activation function sigmoid, we obtain 0.5933. And if we do the same for every node in the network, every neuron in the network, we obtain, so this is the output of the second neuron in the layer 1. And if we move forward and if we further traverse the network, so these two values would serve as an input for the second layer, and we can compute output for the second layer. And output for second layer is in fact the output of the network. So A12 is Y tilde 1 and A22 is Y tilde 2. Clear? Okay. So once we have Y1 tilde, Y2 tilde, we can compute the loss, right? Since output is a vector, we can determine square of Euclidean norm should be simply first predicted output minus actual output square. Sorry, this should be plus. Okay. And when we compute using the vector form, you get what you expect, what you obtain, and you take Euclidean norm of this vector, you get 0.2984. So this is my loss. So nothing fancy so far. We have simply computed the output and loss by traversing the network using forward pass, right? And now we know the loss. Add the output. Let's compute the contribution of loss by each node. And we do this by back propagating this loss from output towards input. Okay, let's see how can we do this. Or how do we do this? So back propagation is the essence of neural network training. We know how to compute forward pass, right? But now we want to compute the contribution of every node towards the loss by back propagating loss. Okay. Okay. Consider a case that we want to compute the partial derivative of the loss function with respect to this weight, right? So we want to traverse the path from the loss function back to this weight, and we need to define a chain rule for these derivatives. So we want to traverse the path. Where is loss? So loss function is here, and we want to traverse the path from the loss function towards this weight. Path would be this. That's how we define the loss function. So loss function depends on the output y1 tilde, y2 tilde. Right? But here, my path towards the weight only includes the output of the first node. So I can relate the pre-activation output with the activation output of the second node using this equation. So Z12 pre-activation output of first node second layer, right? And this is when you pass through this through a sigmoid, you get the output activation output of first node of the second layer, right? And we can relate Z12 with the weight of interest. So Z12 is simply a linear combination of inputs from the previous node. These are the weights, and you add a bias, right? So as I said earlier, output is a composite function of input, right? And if we keep on traversing, so we have this equation from the forward pass, right? So we have a relationship that is defined by forward pass equations. And these equations relate input and output. And now we're traversing back, right? So this is pre-activation output. We pass this through a sigmoid function. You get activation output, which is your output of the first node, second layer. Okay, what do we want to compute? We want to compute partial derivative of loss function with respect to 1, 1, 2. So we have these equations, right? And these equations establish the relationship between loss function and W211, which is this here. So we take this partial derivative. Now to compute this partial derivative, we take partial derivative of loss function with respect to the output of activation output of the node times partial derivative of the activation output with respect to pre-activation input, sorry, pre-activation output. And since Z12 is a function of, it depends on W211, we take partial derivative of this with respect to the weight. Okay. And we can compute these derivatives. So for the loss function, take derivative with respect to y1 tilde. It's a quadratic term, and because of this 1/2, the reason we added here, we get a derivative of the loss function with respect to y1 tilde is simply y tilde 1 minus y1. Right? Similarly, we can compute the derivative of y tilde 1 with respect to z12. It's a sigmoid function. And we know we have a very simple representation of the derivative of sigmoid function. It will be sigmoid 1 minus sigmoid. And using third equation, we can compute derivative of z12 with respect to w211. And we know that when you take this derivative, you only get, this term would be vanished, this will be vanished, you only get a11. Right? And when you compute, when you substitute the values, you can compute the values of these three partial derivatives. How did I compute? In fact, when I had the forward pass, I computed these values. I had these values. I have simply used those values here. So A1, hang on, A11. So I had this output in the forward pass. What about this derivative? I had sigmoid output. I've simply reused it to compute this partial derivative. And I had the true label. I had the output in the forward pass, and which I could use to compute this partial derivative. And when I use these values in this equation, I can get the value of the partial derivative with respect to weight. And this is what we needed. Right? Okay, let's take a step forward and say, now we want to compute for the same problem, partial derivative of the loss function with respect to this weight. Now this is important. So the idea is same. We want to traverse the path from the loss function back to this weight. Where's loss function? It's here. Okay. If you notice, there are two paths from the output to the weight 111. Or if you see it other way, so weight 11 contributes towards loss along two paths. It is also impacting y1 tilde. It is also impacting y2 tilde. Right? Or in other words, this weight is contributing to both the outputs. Okay, let's see in this way, in this case, how do we compute the partial derivative of the loss function with respect to this weight? This is what we want to compute. We first take the path from y1 tilde to weight 11. This is the path. How do you compute the partial derivative using chain? How do you employ chain rule? Partial derivative of loss with respect to y1 tilde, derivative of y1 tilde with respect to pre-activation output, derivative of pre-activation output with respect to the output of the previous node or input to the current node, partial derivative of output with respect, so activation output with respect to pre-activation output, and finally we compute the pre-activation output with respect to the weight. So I have simply traversed this path towards the weight. So first derivative, the derivative of loss function with respect to y1 tilde, and then derivative of y1 tilde with respect to pre-activation output, derivative of pre-activation output with respect to input, this with respect to pre-activation output of this node, and finally pre-activation output and derivative of it with respect to the weight. Clear? Okay, but there's another path, and this is the path. We could also reach from the loss function towards the weight through the second output node. So we also have this path towards weight 111. Maybe you can pause here, and using the notation I have adopted here, can you write a product of partial derivatives with respect to chain rule? So idea same, partial derivative of loss function with respect to y2 times partial derivative of y2 tilde with respect to partial derivative of with respect to a22, partial derivative of a22 with respect to a11. So that's it. Sorry, with respect to pre-activation output first, and then a11, and then a11 with respect to pre-activation output, and finally you have derivative of pre-activation output with respect to the weight. So this will be the total partial derivative of loss function with respect to one weight. Okay, this is looking tedious, right? And this might be looking super complicated, but the concept is very, very straightforward. You simply back propagate, and you will see very shortly, once we handle this in the vector notation, you will have a very, very clear understanding, very good understanding of this back propagation. Maybe at this stage, I encourage you to write down the partial derivative loss function with respect to, say, W122. So this was tedious, right? Let's take a step forward and define this backpropagation using vector notation. And that will have a very compact representation, and that will simplify things for you, most likely, hopefully. Okay, for this neural network, I will start with an example. So for this neural network, we have this forward pass equations. So let me represent these equations and this neural network in an alternative form, right? Just for visualization. Right? So I can have this representation of my forward pass equations. So let me explain. Right? So this is in input layer, right? X. So we're traversing, first obtain pre-activation output, which you pass through sigmoid to obtain activation output. So these two nodes, so these two nodes represent first layer, right? Similarly, these two nodes correspond to layer 2. And finally, these two nodes represent, I should not call them nodes, right? But these two boxes represent the final layer, the layer 3, right? Okay, if you see, where is the contribution of weights and biases? So weights and bias contribute towards pre-activation output. And once you have a pre-activation output, you simply pass it through an activation function G to obtain the activation output. So as you traverse this network from bottom to top, this is a forward pass. Right? And these are the weights which we want to learn. Right? Okay, with this representation in mind, we're going to define the backpropagation using vector notation. So we have this representation. I assume now you're comfortable with this. We compute loss function. How? Using forward pass. For input xi, we traverse this network from bottom to top and compute yi tilde. We know the true label yi, using which we can compute the loss function. Right? And now we have the loss function. We want to update these weights and these biases by taking derivative of this loss function with respect to these weights and biases. And we want to do the same for all the weights and biases. That is, we update weight. This is the matrix of all the weights of the lth layer, and BL corresponds to the vector that contains biases for the lth layer. So we update these two in each iteration using gradient descent by computing the partial derivative of the loss function with respect to the weight matrix. And similarly, we update bias as bias in the previous iteration, the initial value of the bias minus alpha learning rate, partial derivative of the loss with respect to the bias. Okay, how do you compute partial derivatives? And how can we use this alternative representation to better understand the computation of partial derivatives? Okay, let's compute these partial derivatives. And these derivatives computation mean we are backpropagating. Now we want to backpropagate the loss function towards every layer. We want to find the contribution of the loss function towards every node. Okay, let's say you want to find the partial derivative of loss function with respect to W3. I should have a relationship between W3 and loss function. Loss function depends on the output of the final node, right? So the equations that define the relationship between the loss function and W3 are this equation, and equation of the loss function that relates the true label and A3, right? Okay, with this in mind, I can write the partial derivative of loss with respect to W3 as a product of three derivatives using chain rule. Partial derivative of loss with respect to A3 with respect to Z3, and Z3 with respect to W3. Right? If you see this alternative representation, right? So I'm back propagating loss. So I'm traversing in this direction, right? And then once I have the pre-activation output, I know that the waits and buys contribute towards pre-activation output, not the activation output. Right? So once I reach here Z3, I can move in this direction, right? And take derivative with respect to W3. And if I want derivative with respect to buys, so L by derivative of loss with respect to A3, derivative of A3 with respect to Z3. If you compare these two, right, the first two partial derivatives are same because they are coming from this first equation and the loss equation. And the only difference is in when you take derivative with respect to the weight 3, you take derivative of Z3 with respect to weight 3. And when you take derivative with respect to bias, you take derivative of Z3 with respect to V3. Okay. Clear? So this is, we have computed partial derivatives using chain rule. If I ask you to write, to express partial derivative of loss function with respect to W2, how would you proceed? You start from loss function, your target is W2. You move in this direction and you move here. Right? So partial derivative of loss with respect to A3, partial derivative of A3 with respect to Z3, partial derivative of Z3 with respect to A2, partial derivative of A2 with respect to partial derivative of Z2, and now partial derivative of Z2 with respect to W2. If you want for bias, the first four partial derivatives would stay same. Right? So these are same. Right? So only this is changing. This has changed. Right? Similarly, we can move further. In fact, we can go backwards further and find derivative of loss function with respect to W1 and V1. And if I want to compute these, so I should be traversing in this way, moving, and then here. And I assume now you're trained enough that you can write these partial derivatives, right? Okay, let's see another interpretation of these partial derivatives. So this is what we have computed using this alternative visualization. If I rewrite the partial derivative of loss function with respect to W3, I told you that these two, so these first two partial derivatives are same for weight and bias. And in fact, the product of these two represent partial derivative of loss function with respect to partial derivative with respect to Z3. So partial L over partial Z3 times partial Z over partial. Similarly, I can write partial L over, sorry, hang on. It's partial missing somewhere. I will correct these. Okay, yeah. So partial derivative of loss with respect to B3 would be simply partial derivative of loss function with respect to Z3, partial Z over partial B3, right? Similarly, I can compactly represent these partial derivatives, right? So the first four derivatives correspond to partial derivative of loss function with respect to Z2, right? So how do you interpret this? So I'm taking derivative of loss function with respect to pre-activation output of the layer under consideration. So partial L over partial Z2. So this quantity represents the derivative of loss function with respect to pre-activation output of the second layer. And once I have the Z2, I can move towards left. If you remember that alternative representation, I can take derivative of Z2 with respect to weight or with respect to bias. And similarly, I can have for the first layer. Partial derivative of the loss function with respect to pre-activation output of the first layer times derivative of pre-activation output with respect to weight 1 and or with respect to bias 1. Okay. So if you see these equations, in order to compute derivative with respect to weight and bias, we need to develop capability to compute these three types of partial derivatives. The first one is important. For every layer, I want to compute partial derivative of the loss function with respect to pre-activation output. Before passing through activation function. And finally, partial derivative of pre-activation output with respect to weight, and for the same with respect to bias. And we will see very shortly that these two are, I would say, super simple. And you can sense it, in fact, at this stage. Okay. Okay, let's see how do we compute these partial derivatives, these three partial derivatives. If we develop ability to compute these three for every layer, we're done. We can keep on updating weights with these equations. Okay. We first compute partial derivative of the loss function with respect to pre-activation output. We want to compute this for every L, small l, but we compute first for the output layer, the final layer, the last layer. And that is simply given by partial derivative loss function with respect to pre-activation output of the last layer would be derivative of loss with respect to output and derivative of loss with respect to, derivative of activation output with respect to pre-activation output, A over Z. Right. So in some textbooks, so this quantity, partial L over partial Z L, is noted by, so we drop the loss function term, we drop the partial derivatives, we simply use small delta superscript L. And this quantity would correspond to partial derivative of the loss function with respect to pre-activation output of, so Z of lth layer. Right? But we will stick to the notation what we adopted. So we'll use the same notation. Okay, we have computed this derivative for the final layer, but we want to compute it for every layer. Let's see how can we do this. So first we note that how do we compute this for the final layer. So we need to compute two derivatives here. The derivative of loss function with respect to the output of the final layer and derivative of the output of final layer with respect to ZL, pre-activation output. The first derivative depends on the loss function. If we have a regression problem, we can have a squared error, right? Which is simply output of final layer minus true labels. You take Euclidean norm square, you get a squared error. And we know that when you take derivative of this with respect to AL, it's a quadratic term, you get simply AL minus Y. Right? So, you can consider it as a gradient, or it's a simple derivative with respect to vector. If the problem is classification, the loss function is log loss or cross entropy, it will be simply minus Y, so log of AL plus 1 minus Y log of 1 minus AL. So here we're assuming that this is a scalar and this is a scalar. If it's a vector, you can have a transpose and you can redefine the loss function. You take derivative of this with respect to AL, you get a simple representation which is minus Y over AL minus 1 minus Y over 1 minus AL. Okay. So we have computed loss function with respect to the output of the final layer and derivative of the loss function with respect to output of the final layer for both squared error and log loss. Right. Okay, if we use this, we want derivative. We also want derivative of activation function with respect to pre-activation output. So we know that that's how we relate for every neuron, in fact, or for every layer. The derivative with respect to ZL will be simply derivative of activation function. Here we are assuming, so if you recall, we defined that activation function is acting on each entry of the vector Z, because sigmoid is defined for scalar inputs, right? And when I take derivative of sigmoid, we know that it is sigmoid times 1 minus sigmoid. If we have vectors, we want element-wise multiplication. So I have introduced this operator here, this circular dot. This is representing the element-wise multiplication of vectors, right? So we have computed derivative of activation output A with respect to pre-activation output Z, and we've also computed derivative loss function with respect to output of final layer. And if we combine these two, we can get derivative of loss function with respect to pre-activation output of the final layer, this, which we have computed in the previous slide, and times this, which is again it's a element-wise multiplication, because it's a vector and this is a vector, and finally we have this. So we can say we have computed partial derivative of loss function with respect to ZL for right now for L is equal to capital L, only for the last layer, right? but we want to compute it for every L, in fact. In order to compute partial derivative of loss function with respect to pre-activation output of every layer, say for small l, for lth layer, we first observe that I can write partial derivative of loss function with respect to W1 in this form. In fact, we formulated this earlier. Right? In this equation, I'm traversing from output layer towards the weight one. But what's worth noting here, that partial derivative of, say, loss function with respect to Z2 can be written as a product of partial derivative of loss function with respect to Z3 times derivative of Z3 with respect to A2 times derivative of A2 with respect to Z2. Similarly, so this first two quantities, first two terms represent, in fact, first four terms represent partial derivative of loss with respect to partial derivative of Z2. And I can use this to compute partial derivative of loss with respect to partial derivative of Z1 by simply multiplying with these two terms. So observing this, I can rewrite, in fact, I can relate the loss function derivative with respect to ZL in every layer in this form. So partial derivative loss function with respect to ZL would be equal to partial derivative with respect to ZL plus 1, derivative of ZL plus 1 with respect to AL times derivative of AL with respect to ZL. And if you observe this relationship in this equation, you can see that this relationship is exhibited by this equation above. Right? So derivative of pre-activation output of the layer with respect to the input of the current layer or output of the previous layer. Right? So we can write as ZL plus 1. We know that ZL plus 1 is WL plus 1 AL plus BL minus 1. Right? This is simple forward pass equation. Right? AL is the output of previous layer and ZL plus 1 is the pre-activation output of the L plus 1 layer. If I take derivative of this with respect to AL, what do I get? WL plus 1. Right? So this term would be discarded and you only have WL plus 1. So if I use these results, I can write, so this equation can be equivalently formulated in this form. So derivative of loss function with respect to ZL would be equal to, so derivative loss with respect to ZL plus 1. So you get WL plus 1, right? Times partial derivative of loss with respect to ZL plus 1. And we know that derivative of A with respect to Z would be simply given by the sigmoid function, derivative of sigmoid function or derivative of activation function. And we are again using the element-wise product here. And I have changed the order here to keep the consistency of multiplication of matrices. Right? Okay, let me explain this again very quickly. So this term is coming here. So partial derivative of ZL plus respect to AL is here, and I've used this result to note this here. And finally, A over ZL would be simply G dash of CL. And we are using element-wise multiplication because activation function is acting on each entry of the vector. Clear? Okay, finally, we have this very, very important relationship. Right? And using this, we can compute derivative of loss function with respect to pre-activation output for every layer. And it simply needs the weights in the next layer times derivative of loss function with respect to pre-activation output for the next layer times derivative of activation function. In fact, we have computed this for the final layer, and using this and using this equation and derivative for the final layer, we can keep on traversing backwards and we can compute this partial L over partial Z L for every L. L is equal to L minus 1, then L minus 2, and L minus 3, and so on and so forth, because we have already computed for L is equal to capital L, right? Okay, now we want to compute derivative of pre-activation output of layer with respect to weight or bias. And this is super simple. If you recall, we started with a case that we should have a capability to compute loss function derivative with respect to pre-activation output and derivative of pre-activation output with respect to weight and bias. We have computed loss function derivative with respect to pre-activation output, ZL, and now the rest is we want to compute derivative of pre-activation output with respect to weight or bias. And we know that forward pass equation, and we take derivative of this with respect to W, you simply get AL minus 1. And take derivative of this with respect to bias, you simply get 1. As I said earlier, so these two derivatives are super simple. They are very easy to compute. A very simple interpretation. Okay. So finally, we obtain partial derivative of loss function with respect to weight of LF layer would be this, which we have computed earlier, and times this. And when you use this here, I have used transpose again to make sure that when we multiply matrices, the dimensions are consistent. Right. Similarly, partial derivative of loss with respect to BL would be equal to, in fact, derivative of loss function with respect to pre-activation output. And if I sum all this together, the key equations for backpropagation in vector form would be simply, so these two equations, derivative of loss function with respect to weight, derivative of loss function with respect to bias. And both equations require derivative of loss function with respect to pre-activation output. And we know that we can compute this recursively. We can by starting from the final output layer and moving backwards. And the base case is for the final layer is derivative of loss function with respect to the output of final layer. And we also have the equation for this for regression case, and when we use squared loss, and classification case when we use log loss. Right. For sigmoid activation function, we know that G dash would be simply sigmoid element wise 1 minus sigmoid. Right. Okay. This is a summary of the key equations. Let me also give you an interpretation of key equations using the alternative representation of the network we had. So these are the weights and biases. Here they're contributing in layer 1, here they're contributing in layer 2, and here they're contributing in layer 3. And we have these three key equations for backpropagation. So using this equation, I first compute the base case, partial derivative of loss with respect to Z3. And using this, I can compute partial derivative of loss with respect to Z2. And using this, I can compute partial derivative of loss with respect to Z1. Right? So if I use this in here in this equation, I can obtain this. And when I use this here, I can compute this, right? And once we have derivative of loss function with respect to pre-activation output, I can simply multiply with AL minus 1 or use it as it is to determine the partial derivative of loss function with respect to weight and bias, right? Okay, let's see. We have a regression problem and we assume squared error and sigmoid activation function. And let's see if it all makes sense. And that the equations we have are consistent with respect to dimension of the problem. For example, we can want to compute derivative of loss with respect to weight 1. And we know that this is given by derivative of loss equal to Z1 times derivative of Z1 with respect to W1. The base case is this. Derivative of loss function with respect to Z3 would be this times sigmoid derivative. Right? And if you're squared loss, this would be AL minus Y, right? And this would be simply a derivative of the sigmoid. If you ask the dimension of this, in this example, this quantity is a scalar. Right? And now this using this base case and the key equation, I can compute derivative of loss function with respect to Z1. It will be simply this derivative of L with respect to Z2, which I again use recursively to relate with the base case. And now, what is G dash of Z1? So Z1 is pre-activation output of layer 1. There are 4 nodes. So Z would be vector and sigmoid is acting on every entry of the vector. So the size of this would be 4 times 1. What about G dash of Z2? 3 times 1, 3 nodes. Right? Partial L over partial Z3, it's a scalar. So this is 1 cross 1. And this weight W3 is, what about W3? Which is here. 3 inputs, 1 output. This is 3 cross 1. So 3 times 1 times 1 cross 1. So this quantity will be 3 times 1. So we multiply element wise, you get 3 times 1. Right? So W2 transpose. So what is size of W2? 3 cross 4. So W transpose would be 4 cross 3. So 4 cross 3 times 3 cross 1, and this is all dimensionally correct. Right? And finally, we know that when you take derivative, so what you get is 4 cross 3, 4 cross 1, multiply element wise, you get 4 cross 1, right? So you get partial derivative loss with respect to Z1, but this would be 4 cross 1. And when you multiply this with A0 transpose, which is 3 inputs, right? 1 cross 3. So 4 cross 1 into 1 cross 3, you get derivative of loss function with respect to weight 1, which is 4 cross 3. And we know that W1 is 4 cross 3. And therefore, we can use this to update W1. Right? So I think it's all makes sense. So concluding, so these are the key equations we had for back propagation. So this is the base case. Using this, we can compute derivative of loss function with respect to pre-activation output for every layer. And when we multiply this with AL minus 1 or use it as it is, we can compute partial derivative of the loss function with respect to weight and with respect to bias, or the contribution of loss function, or the contribution of every node, a contribution of weights towards the loss function, right? So we stop here. So that was about neural networks. Time permitting, I will review very briefly deep neural networks, which is in fact deep learning. In the next video, we will start with a new topic, that is unsupervised learning, and we will focus on clustering in unsupervised learning. We'll stop here and we'll continue in the next video, inshallah. Allah Hafiz.